I like to call myself an astroparticle theorist. And maybe some of you are not familiar with what we call astroparticle. That's essentially saying that we want to study the fundamental laws of nature when we try to perform cosmological and astrophysical observations. So we try to learn from the sky what fundamental physics is. And I'm not a Mond fan, not somebody that knows Mond in detail, I would say. And in my perspective, Mond as an effective theory of gravity in some given regime is not so interesting from my perspective, in the sense that it doesn't open me a window to learn for fundamental physics. And so in this respect, I haven't studied it in detail, and I'm not planning to work on it. So what I'm going to give you in these 3 lectures is a perspective on the dark matter problem from a particle physicist or an astroparticle physicist. So the dark matter problem is something that has been sedimenting in the years. And it's something that, for instance, I tackled in the beginning. When you start a PhD, you are given a problem, and you are not looking at the grand overview of the problem. You are looking at one fine detail and trying to get the most out of it. And I tackled the dark matter problem from this narrow perspective, which came from particle physics, saying that in the standard model of particle physics, there's something we don't understand, and we have a solution for it. And as a byproduct, that solution is providing a dark matter candidate. So that's a beautiful motivation that somebody that in the 90s went to conferences on supersymmetry heard 30 times in the first 2 days. So I was working on supersymmetry. I was computing 1 loop and 2 loops diagrams for a specific method to detect dark matter. So that's the way things were working back in these days, which now are getting old days, unfortunately. But that's not the perspective I suggest to my PhD student now. So the perspective I suggest to my PhD students now, it's more on the line of what I'm going to tell you in this week. And it goes more or less like this. I think we have to be knowledgeable about how the issue has been developing. So in this first lecture, I will tell you something more essentially about things that have already been mentioned in the previous lecture, giving some formulas and some numbers. I like to give numbers because the dark matter problem is not some vague issue. It's an issue in which numbers are pretty precise. So I'm not going I'm not an historian, so I wouldn't be able to give you a review which has an historic imprint, but I will try to give you a sense of what this does make sense with our eyes today. So I will start from Zwicky, who was already mentioned, and then I'd like to mention today to you about modern ways that we have to learn about dark matter from, so to speak, standard astrophysical probes. So the shaping has already been mentioned today. The real shaping of dark matter problem in a modern view has come instead with cosmology and the standard model of cosmology. The standard model of cosmology is something which is an effective theory, is not something which contains, well, it contains some fundamental physics, but not all fundamental physics. But it's something that essentially has very few parameters, I would say. So it's describing the universe with 6 parameters. And these 6 parameters have been overfitted in the sense that now when you look at the data from cosmology, it's more the error that are connected to the way you're doing measurements rather than to the fact that you have to collect more statistics about a given measure. So, and in this sense, it's a marvelous story in the sense that once you introduce this stuff which you don't know, things seem to work from the infancy of the universe. So you have quantum fluctuations in the very early universe, which turn out to be the structure we see in the universe today. And this route, as I said, is coming in with very few assumptions. And I don't consider it outrageous if on top of these few assumptions, we are adding in something more if there are some glitches at the end of the story that don't quite work. So, but that I will discuss in what sense. So this is this second point. And then this is the path that I suggest also to my students in a first class of dark matter studies, because I think that in these 2 steps, there are actually many information that one can drive out when you want to put this story on a perspective which is the perspective of a particle physicist. So a particle physicist would need to attach this problem saying, okay, I need to understand what is the energy involved in the problem. I need to know what is the particle mass. And I need to know how this particle is interacting with other particles. So I need to know a mass scale, an energy scale, and an interaction scale. And then although there is this nightmarish cloud of different possible models that one can apply, those clouds is not coming in, say, an arbitrary tree. There are different branches that one can take in this tree, and those are sort of dictated by these first 2 steps that I mentioned here. So I would like to try to appreciate that is not really a free game in which anybody can start doing anything. And then I will come to this last point, which is some examples. And historically, these examples, I would say, that are dictated by some kind of prejudices. So I mentioned you the fact already of supersymmetry and supersymmetric dark matter candidate. That came from a prejudice that particle physicists had of not being able to understand the hierarchy problem, why weak scale physics lives at the weak scale and not at the Planck scale. So that's a complicated story, but is just to say that it's not a scale which we are naturally predicting to be there. So we want it to be there for some reason, and supersymmetry is one of the reasons for which it was there. So, but that is setting you really on a narrow lane. And there are a few narrow lanes you can take based essentially on two kind of prejudice. How you want to solve, say, shortages of the standard model particle physics, and this is the first prejudice, and orthogonal to this, but not too much, is the fact that you want to have understanding at a fundamental level. So understanding at a fundamental level is to say how you put dark matter in the universe in the first place, how you generated dark matter in the early universe. And that again sets you on some paths which are less narrow than the other route, but still are definite paths. And we are sort of in the era in which this kind of approach based on these two main prejudices is fading away, and we are more trying to link ourselves to phenomenology also when I do a description of dark matter in terms of particle physics. So let me start. And I want to start from this, which is a kind of prologue which should come at the end, but I want to put it at the beginning because it's the following idea that the picture that I'm addressing is kind of contradictory in the sense that I'm talking about something I have no clue about what it is in reality. There's no one single observation which is pointing me to a specific particle physics scenario. So I have that a significant fraction of dark matter. So of course I'm starting in agreement with a set of observation, and I have a set of assumptions, of course. Once I do that, I will specify both. I'm on a path in which I conclude that a significant fraction of the universe is in some form of matter which is exotic, is different from anything that I've been able to detect in a lab so far. But at the same time, I'm saying that this component here is very precisely known, at least in how much I need it to be there. So, and the way cosmology like to express this number of what is the total mean density, total mean mass density of dark matter is this parameter here, omega, which is just taking the mean mass density and normalizing to the critical density of the universe. What is the critical density of the universe? In the standard model of cosmology based on Freeman-Robertson-Walker metric, there is a number, this critical density, which corresponds to the fact that the geometry of the universe is a flat geometry. And we know from observation that we are in that configuration, or very close to that configuration. So in terms of this ratio, we have determined the density, or the mean mass density of dark matter to be a number which is known to better than 1%. So there are two parameters here. There is also h, small h, which is just the expansion rate of the universe in some units. And I would like to emphasize a little bit how big or small is this number, which corresponds to the critical density. And since I told you that I want to be quantitative, every now and then I will have to explain you, if you are unfamiliar with this, about units that I'm using. So here I express mass density in terms of electron volts per centimeter cube, which is a way that the particle physicists would like. And when I will mention measures of masses in my lectures, I will go back and forth between what particle physics like and what an astronomy or astrophysics like. So a particle physicist uses mostly a system which is called the system in natural units, in which I'm fixing the speed of light to be 1. And then I sort of use interchangeably energy and mass. And then I specify masses in terms of this electron volt. The abbreviation is this EV, which has some technical definition, which is not very interesting. but which I want to put on a physical ground, telling you that if I want to weight particles I know, in particular the stable particles that are around in the universe, stable particles that are around the universe are either leptons or electrons, or are baryons, protons, and helium. And an electron is weighing about 500,000 electron volt, while a proton is weighing about 1 billion electron volts. The neutron mass is roughly the same. When I scale up in atomic number, I get to an element which is made of 2 neutrons and 2 protons, I get roughly 4 billion electron volts. So this is opposed to what an astrophysicist would do, which is by convenience weighting masses into something that has to do with astrophysics, and most likely the solar mass, which is this huge number in terms of a particle physics scale. So going back here, I have a number which is telling you that roughly the mean density of the universe is something like 10 to the minus 5 protons per centimeter cube. So it's a pretty small number. And out of this small number, when I plug in this number and this, I get that about 26.4% of the universe is made of this exotic stuff. And if I compare to the total mass of, total mean mass of the universe, I have 2 parameters in the standard model for cosmology, the dark matter mass and the baryonic mass. This baryonic mass is what is made out of things that I found in labs, so electrons, protons, heavier elements. But since the electrons is weighing much less than the proton, is a good approximation to say that the stuff we know in the universe is mainly made of hydrogen and helium. And still, when I put the two together, this part here is about 85% of the total. So this is the goal, and as I mentioned, this is a long-standing problem, which I mean, if you want to have a view which is more historian-oriented, my friends Bertone and Hooper have written a review which is kind of nice. So let me go to the story of Fritz Zwicky, some man with a character, which is part of the story that is behind the fact that Zwicky is so well known for the discovery, in inverted comma, of dark matter. So what Zwicky did was the following. This was very kind of soon after the discovery of external galaxies. We used to call them nebulae. In 10 years before, there was the starting of operation of a larger telescope in Southern California, Mount Wilson, on which Edwin Hubble was able to resolve the fact that the lumps in the sky, which looked like some clouds of gas, were not gas, but they were stars that were grouped together in a galaxy that had to be pretty much analogous to the galaxy inside which we are sitting, the Milky Way. And he was able to do that because he had identified some special stars inside this galaxy, which are called Cepheids. So these are stars in which are variable, and the period of variation of the star is connected to the luminosity of the star. So observing the intrinsic luminosity, so measuring the period of the star, you could understand how bright an object is emitting light, and then measuring how bright it looks in the telescope, he was able to understand how far the object was. So then he concluded that the Andromeda Nebula was an external galaxy. And then he started piling up distances and the speed for these objects. So the speed was derived in another clever way, which is the fact that he was observing these objects with an optical telescope. And in a telescope, an optical telescope, you can split the light, the optical light, into its different colors. And within these different colors, elements that are sitting at the surface of the star are absorbing or re-emitting light with a frequency, with an energy, which is just set by the transition line of the given element. So he sort of knew where these lines were standing, but what he was noticing was that in the observation, these lines were going more and more to the red part of the spectrum. They were redshifting. And then he correctly interpreted the fact that this is due to the fact that these objects are moving away from us, and then there is just some Doppler effect, which we are familiar with, for instance, in acoustic physics. So there was this collection of objects for which it was measured the distance and how far they were moving. And then Zwicky came with this paper, which was written in Deutsch, so I cannot translate. But would I be able to translate? The title reads, the redshift, the shift to the red in the spectrum of these extragalactic nebulae. So this is a paper in which dark matter is not mentioned in the title nor in the abstract. However, the most interesting observation that is in this paper is the fact that these nebulae were going into this diagram of velocity versus distance with some clumps. So there were objects which are sitting one close to the other. So at the distance, which was very, very, very small in this huge scale, but with velocities which had a dispersion that was kind of large. And in particular, there were 8 objects associated to one of these clusters, which was called the Cloma cluster. And what Zwicky interpreted in this paper was the fact that if there is this system is a system which is closed, self-gravitating, and somehow in equilibrium, you can use the virial theorem to derive what is the total mass of the system. This total mass looks large because there was a large velocity dispersion. So we go to the argument now. I just want to mention that soon after this paper in 33, actually people did realize that this was a big issue. This was a paragraph in the other paper, but then there was a series of papers in which people were trying to understand this fact that you could measure masses of clusters of nebula out of this method. And this Zwick himself applied a more careful calculation on COMA 4 years later, but there was also an analysis of another cluster of galaxies, the Virgo cluster, which is actually the closest cluster to us, done by some other astronomer, Smith, and this was kind of refined in the years. So what were we doing? Okay, so this is an optical image of the COMA cluster. And okay, and here you see there is some system of stuff, which from an image like this, you are not able too much to appreciate. But if you combine this image with the estimate of the distance of the single objects that you have here, you can appreciate that there are some of these objects that are standing just in the field of view in front of the COMA cluster. But then there is a collection of many of these objects, as many as 1,000, which sit in a size which has roughly a radius of 1 megaparsec. And these are moving with a velocity of 1,000 kilometers per second on average, with a dispersion velocity of 1,000 kilometers per second. So again, I want to be quantitative. So what's this measure of distance I introduced? The parsec is an abbreviation of the parsec is PC, is a measure of distance based on the parallax phenomena, which is the following phenomena. So suppose you are looking at a star which is sitting somewhere at a distance which is not too far compared to much more distant stars. The position of this star in the sky, so compared to these stars that somehow are sitting very far away, will change during the year just because of one simple fact, which is the fact that you're looking at the star from the Earth, sitting on the Earth, and once you're pointing to this star, the Earth is making a revolution around the sun, roughly circular orbit, and then the projection on the background of this star will change whether you are sitting on this side of the orbit or that side of the orbit. So the parsec is this ideal case in which the distance of the object is such that this angle here, which is describing this circle of the star on the background, has an aperture which is 1 arcsecond. So to convert this distance into some physical distance, you just need to know how far we are sitting from the sun. And then it turns out that the parsec is around 3.26 light years. Once you put in this fact that we are sitting at this distance from the sun, or if you like to be converting from an astronomical unit into a CGS particle physics unit, parsec is about 10 to the 18 centimeter, 3 times 10 to the 18 centimeter. So again, I want to put this on scale. So what does it mean? The closest star to us is Proxima Centauri, and it's sitting at a distance of 1.3 parsec. We are sitting in a galaxy, the Milky Way, sort of in the outskirts of this galaxy. So not really on the border of the stellar disk, but nearly. And then our distance to the center of the Milky Way is about 8 kiloparsec. Then I was telling you about Andromeda, this galaxy that Hubble had discovered is sitting away outside the Milky Way. And in fact, if I measure it in parsec, it's standing at a distance which is around 800 kiloparsec. And Andromeda is the closest major spiral galaxy. And then we come to the Coma cluster. The Coma cluster, which Zwicky was studying, is sitting at about 100 megaparsec. So there is a hierarchy of scales. And I close up this hierarchy telling you that, okay, I'm not going to tell you how you estimate this, but the size of the visible universe is something like 30 gigaparsec. Okay, so now we're back here with this 1,000 galaxies that are compressed on a radius which is not too large, because this 1 megaparsec is saying just 2 orders of magnitude larger than the size of, say, a spiral galaxy, the visible part of a spiral galaxy like the Milky Way. And these galaxies are moving with this velocity, which now I will argue that is fast. So what Zwicky did was to apply this virial theorem, which goes like this. I have a system, and I suppose that I have an equilibrium between the potential energy and the kinetic energy. So the single objects are balancing the gravitational pull with the fact that there is some kinetic energy associated to any of them. And the virial theorem, which was known at the time from the physics of gases, and which was actually applied to astronomy for the first time by Zwicky, it says that the balancing, it goes like this, that the potential energy plus twice the kinetic energy is in equilibrium. So there are ways to estimate the potential energy and ways to estimate the kinetic energy. And what is appropriate for the kinetic energy is to use a non-relativistic formula. So this 1,000 kilometers per second is still much smaller than the velocity of light. So you have what you are familiar with from classical mechanics, that the kinetic energy is half the mass times the velocity squared. So then I'm doing some average. And then I'm multiplying by the number of objects that are in this system. The potential energy is here described under some assumption. So the assumption here is that gravity in the Newtonian limit is valid for this system. And then you know that the potential energy in a Newtonian gravity is just the g Newton times, so this is the potential energy for a pair of these objects. So the mass of one object times the mass of the other objects divided by the typical distance from these objects. And then I just have to sum up how many pairs I can do with n objects. And this number of pairs is n squared divided by 2. So then I can close up the thing, because if I want to estimate what's the total mass in the system, I just have to multiply the number of the object times the mass associated to a single object. And those I can, the two things I can read out from putting these two formulas inside here and then extracting one of the mass. So I get that this is of the order of twice the typical size of the object times the mean velocity squared divided by g Newton, and then I just have to plug in numbers. So I said that this is 1 megaparsec, so it's 10 to the 6 parsec. This velocity is 1,000 kilometers per second, so it's 10 to the 6 kilometers per kilometer squared second minus 2. This is g Newton in the same unit, which I can convert to grams and then to solar masses, getting this number here and this using this relation that I wrote before for you. So this, as Vincenzo was asking, is not really the number that Zwicky got, because the numbers I'm giving you here for the Coma cluster are modern numbers. So what he had was an angular size of the object. The angular size gets into a physical size if you know how far the object is. If you have underestimated, if you are overestimated the distance, as we actually Hubble had done, then you get slightly wrong numbers, but still were numbers which were far off with respect to the fact that Zwicky was kind of assuming that a single galaxy was made of stars, about 10 to the 9 stars. So he had to have a weight which was about 10 to the 9 times the mass of a star, so typically a mass of the sun. So if you make this exercise, this same exercise, with modern ways of measuring, of mapping galaxies into a galaxy cluster, surprisingly, you get this measure here of a mass to light ratio, which is light here means the luminosity associated to stars in that object. You get a number which is about 160 mass of the sun divided by luminosity of the sun, which if you have some way of measuring this total stellar luminosity of stars in the universe, and there is some way of making this kind of census, you get a number for the average mass density in the universe, which is this number here, which is kind of close to the number that I had in my prologue slide. Okay, then yes, yeah, yes, yes, correct. So that's actually an interesting point, because I would like now to dig a little bit deeper in what I just did. So, because now, okay, Zwicky starts talking about dark matter. Of course, he didn't have in mind any kind of exotic particles. But what is really visible versus invisible in this exercise I just did? So the procedure I followed has to go through a set of steps, which I wrote here. So the first step is to define your model. And your model comes with some assumptions. There are three main assumptions that are coming in. The first is that the system is closed. It's a self-gravitating system and is in equilibrium. I can apply the virial theorem. The second assumption is that this system obeys gravity under Newton's law. the third assumption is that I want to try to associate the mass to what I can directly sort of measure. So I associate mass to the, say, luminous stars, or if you wish, it was measured in nebulae, so collection of stars in galaxies. So this is the model. But then you have to somehow track the model. And there are two extra steps. So you have to identify in your observation what is the tracer that is testing your model. And then Zwicky was saying that galaxies are the dynamical tracer of his model. And then, okay, the tracer is something that comes with a way of observing the stuff. And he had only one choice here. So he had the Mount Wilson telescope, which is measuring just optical light. And this optical light is what in modern terms is called the messenger of my observation. So this comes with this feature that this messenger has this color spectra, and I have a definite pattern to extract the physical information out of this color spectra. So then you do your exercise, and once you get to the end, you get to a point in which the pattern is inconsistent with some of went through this, of you went through. And okay, so as a matter of fact, you can blame any of the steps, but the step which was blamed was the first one. And at the time of Zwicky, the blaming was mostly on this first point. So astronomers started questioning about the fact that the system was in equilibrium. Maybe these galaxies that whose redshift was measured were some outliers, which were sitting in the galaxy cluster for a short time, were not really bound to the system, and we were going just to escape from the system. So that okay, turned out to be in contradiction with the fact that these galaxy clusters are actually a stable system over a period of time, which is much larger than the time it would take for this fast-moving galaxy to escape from the system. So, but then, okay, that's what we do in physics. We test one hypothesis, something doesn't work. We try to understand what's wrong in our hypothesis. So for Zwicky and his contemporary people, it was this one. For us, as we were discussing even earlier today, you can either blame Newton's law, or you blame the fact that you are wrongly associated the mass to what you can actually measure in this exercise. So, but this is actually not taking you very far. And I would say that even buying the hypothesis of dark matter, which at this stage you may very well not do, this analysis is really giving a little room for actually further steps in saying I identify the nature of dark matter. And this step has to do also with the extra two ingredients that I put here, the tracer and the messenger. So let me try to dig into this and put this thing in a more modern perspective. So I think that there's full consensus now that what we want to try to address the dark matter problem with is not some particular aspect of it, but it's really trying to be the broadest possible in the way you assess it. And one part of it goes through the fact that we are really in what is called the multi-messenger era. Anybody that wants to introduce, to fill in a grant proposal in astrophysics and send it to ERC, the keyword multi-messenger now is kind of needed. Okay? But for good reasons, I would say. And in fact, I mean, when Zwicky was looking at the sky, he was looking at the sky in optical frequencies, and in a narrow window which stands here or here in the spectrum. Now, with this cartoon is about the fact that when you're considering a messenger, a photon, photons comes with an energy or equivalently with a wavelength, which spans a spectrum which is really way much larger than optical photons, which are sitting in this narrow band here. So you can go to higher energy or smaller energy. In energy is equivalent to saying wavelength. So this is a wave with a different, with a given size of oscillation, and this size of oscillation can go from say microscopic when you are in the radio to finer than the Fermi scale when you go to the TV energies. All of this is interesting because it's not really equivalent to say I look at a galaxy cluster in an optical wavelength, or I look at the galaxy cluster with a photon that comes at ultra high energy. First of all, from a practical point of view, is not really the same, because observation in the optical and in the radio can be done straightforwardly with a telescope on the Earth, while what is plotted here is the probability of absorption of a given photon through the atmosphere of the Earth. And then you see there's a huge atmosphere when you go to ultra long radio wavelength, and when you go in this spectrum here of X-rays, and even going to larger and larger energies, you are limited by the atmosphere. So effectively, okay, we have eyes that detect optical photons because we have adapted to what gets to the crust, to the surface of the Earth, while some extraterrestrial with X-ray eyes wouldn't see anything because X-rays are not penetrating the atmosphere. To measure X-rays, you have to build a satellite and go outside of the atmosphere. The same way that to measure TV or PV gamma rays, you have to go either with an instrument that is flown in the atmosphere at some altitude, or again to a satellite. And also, so that's for the Earth absorption. There's also absorption that or modification of your messenger, which could come in with other phenomena. And for instance, what this slide is about is that it doesn't make any sense to try to make astronomy with gamma rays if you're going to energy of the gamma rays that are getting larger and larger. Just because very high energy photons emitted in a distant source get absorbed by the fact that they don't travel to us in the vacuum, but they traveled into the intergalactic interstellar medium, which contains low energy photons. And then what happens in a beautiful quantum field theory is that a photon of high energy and a photon of low energy can transform itself into a pair of positron and electron. And to understand why, when this is efficient, you have to do this little calculation of relativistic kinematics. And okay, the end of the story is that if you have a photon that is sitting in the background, which is an infrared photon, and there are lots of infrared photons in the interstellar medium which have been emitted by stars. So these photons are absorbing TV photons. So what's plotted here is a plot in which on the horizontal axis there is a redshift which is pretty much like saying distance if this z is much smaller than 1, and it's telling you how far out you are going to get a signal from a source depending on the energy of the photons that are emitted in the source. And you see when you are here at TV, you are just limited to the local universe. When you are at PV energy, you are not even seeing the galactic center. So you have to be, when you do the exercise of trying to understand observationally what is the universe made of, you have to understand what are the limitations with your messenger and your tracer. So just a little bit more, and then I stop. So then people have gone away from photons as messenger. One can take other stable species as messengers. So you can take charged leptons, protons, and nuclei. So a set of electrically charged particles, which we usually call cosmic rays. So these are interesting because cosmic rays are accelerated in galactic and extragalactic sources. We have measured the spectrum in some detail on a huge energy scale, which goes to some kind of low energy on which we are limited from the fact that we are sitting in the solar system, to a high energy that again is coming in from the fact that again these ultra high energy cosmic rays can get absorbed in the interstellar medium. So there is a cutoff here at 10 to the 20 electron volts, which is telling you you can use this messenger, but not at energy larger than this. So it was few TeV for the gamma rays is 10 to the 8 TeV for the protons, but still that's the range that from first principle you can understand you can use for your experiment. So there's one extra caveat, which is as to the fact that with cosmic rays, since they are electrically charged, they are deflected by magnetic fields. There are magnetic fields in the galaxy and even outside galaxies. So the tracing of cosmic rays from the source can be more complicated than for gamma rays. Another messenger that people have been trying to exploit are neutrinos. Neutrinos are the most elusive, again, are stable species, but they are the most elusive ones in the standard model of particle physics. So we know well how they interact. They interact only via weak interactions. Well, there are three kinds of forces in nature: the electromagnetic, the strong, and the weak force. And neutrinos are subject only to the third. We don't know their masses. We have some upper limits, and what we know is that neutrinos are light. They are much lighter than the other, so to speak, matter particles that are at disposal in the standard model of particle physics. So they interact very weakly, so there's not a problem of absorption by a background, which I mentioned in the previous two cases. They are not deflected on magnetic field. They are copiously produced in sources, so they are kind of the perfect messenger, except that they are very challenging to detect for the same reason that they interact weakly. So if you want to do astronomy with neutrinos, you have to build huge detectors, which people have been building in the last year, like the ice cube detector in Antarctica, and they have been entering the multi-messenger era with some speed now. And then, of course, there is this last pillar of this multi-messenger game, which has been played by gravitational wave detection. And this is a chapter, I guess, in this call will be dig further because, okay, since the first detection of LIGO and Virgo, there are now more than 90 events that have been detected from this specific phenomena of merging of binary system of two compact objects. These compact objects are mostly black holes. There are a few cases of black holes, neutron stars. And then there is this exceptionally important event in which we think there was a fusion of a pair of neutron stars, because this event has been gone ahead with a lot of signals that come in from all the messengers that I mentioned before. Really, there is, if you look at the electromagnetic spectrum on most wavelengths, there's been something going on. And this is an incredibly rich wealth of information that comes in with this single object, and which to my mind should be the same kind of attitude that we have to implement for anything that we do not know, such as dark matter. So I took this time for this side topic, because now I want to go back here. So we had this beautiful optical image from Sloan of the coma cluster. This is a beautiful image, but this is not the image which you want to use if you want to trace the matter, at least the standard matter in this system. Because now if you switch frequency and you go from optical to X-rays, okay, and again, this is a modern image, but this has been going on since the time when people sent satellites to measure X-rays, so in the late 70s. So on top of the light distribution, there is a bulk of radiation here, which is showing up in X-rays. And this bulk of radiation is telling you that most of the ordinary matter in the coma cluster is not actually associated to star, but is associated to gas, hot gas, which is emitting in X-ray frequencies that are, these X-rays are produced by a phenomenon which is called Bremsstrahlung. So this is a gas which is hot and is ionized, and then you have sort of the scattering of electrons, these fast electrons, on the electric field of the ionized nuclei. And so the bend over that the electrons get through the scattering is resulting in an emission of X-ray. And then, okay, that's actually a better messenger if you want to at least map part of the mass in this system. So out of this radiation, you can do an exercise which is more powerful than the one with the virial theorem. So the intensity of this radiation is telling you on the line of sight how many electrons you have, and then you can measure the temperature of these electrons from the spectrum of the X-rays. So out of this, essentially, you can sketch a system saying that is a pressure supported system for this hot gas. So this hot gas is something that would like to expand, dilute because of the internal pressure associated to it, but it cannot do it because it's confined into this gravitational potential well. And then you can write up an equation which is the equilibrium equation for this system without going into much detail. The equation is an equation in which essentially the only unknown is the mass distribution in the system. Again, assuming that Newtonian gravity is what governs this system. So out of this, you can measure how much mass is in, now I call it baryons. So most of the baryons in the system is in the gas. The amount that is in stars is negligible. So the ratio between the amount of mass which is in baryon to the total mass is, again, you can do it on a specific system, and you get a number that if somehow you know what is the mass of baryons, the average mass of baryons in the universe, you get again an estimate of the total mass in the universe, which is exactly in the right ballpark. So this exercise is telling you that as a tracer of mass in the universe, galaxy clusters are actually a good tracer. So even more modernly, the way you can trace the distribution of mass in a system which is compact and very massive is using gravitational lensing. So Einstein theory is telling you that gravity is a form of perturbation of space-time, and then light will follow shortest path into this perturbed space-time. We follow geodesics, and close to a very massive bodies, they would just bend in the same way that an optical lens makes light bend. And okay, you have spectacular images like this one, in which what you're seeing here is some kind of galaxy which is sitting in the background with respect to this galaxy cluster, and seeing it through this gravitational lens, you see multiple images for this galaxy, whose image is deformed on arcs in the system. So you can use again a theory, general relativity, to reconstruct what is the distribution of mass in the so-called lens, and then reconstruct fairly precisely some mass profile, which is in good agreement with the other methods that you had to estimate the mass in a single galaxy. Actually, this is very spectacular because it works not just on single objects, but it works on the structure of the universe as a whole. So we think that the universe is made out of patches in which high density of mass comes at the intersection of filaments, and out of gravitational lensing, now not This one is called strong lensing because it's a single lens which you reconstruct in detail out of a tracer. You can do what is called weak lensing, that is look how the images, the shapes of a given set of tracers gets deformed while it propagates through some matter distribution. So if you have a census of how the shape on average of galaxies should look like in the sky, and you measure a different pattern when it's lensed out, you can make a reconstruction of the distribution of mass in front of the pattern that you are seeing. So you can really do mass tomography out of this, and there are really spectacular results out of this. So I think that I'm going to switch to galaxies now. So if there are questions, was it this too technical? So I lost all of you, or please.
Not part of the conference because I received a very important phone. Can you say something more about the possibility to detect something about dark matter through gravitational waves?
So I think that so you see most of the early events were events referring to merging of black holes. So the mass range, so these are black holes of a given mass. Usually there is some hierarchy between the two masses. But these instruments are kind of more likely prefer to detect some kind of mass ranges. And it came as some surprise, I would say. In the beginning, this estimate of black hole masses that we were observing, they were kind of too massive with respect to the standard lore in galaxy in galaxy and star formation that was up to say 2016 or so. So there were a lot of speculation on whether this could be a signal that these are not objects that are formed in galaxies, but are objects that are primordial. So the detection of gravitational waves has revitalized a lot a field which is connected to dark matter being primordial black holes. And there's a lot of interesting research connected to that. There's a lot of interesting research also connected to the fact that black holes are supposed to be the place in which there is the highest concentration of dark matter in the universe, because there are some mechanisms over which, although dark matter is collisionless, it sort of gets focused in these ambience with densities that are much larger than the density of say local dark matter. And then there's some quite a number of phenomenological observations that you can get out of that. And it would be really fantastic if we could get some more events of this kind, in which in some detail you can model the progenitors of the gravitational wave event, because dark matter can influence the evolution of these progenitors. So there are a lot of things that one has been
already enough to precise detect these kind of events. Not necessarily Einstein telescope.
No, sure. This is a process which will come with statistics. So we need many more events. So this event was kind of a lucky one in the sense that it's relatively close to us. And then, yeah. Any other? So then there is the other part of the other main part of the story, which comes from classical astrophysical observation, which is the one that regards galaxies. So I told you that clusters are to some extent a good tracer of dark matter in the universe. So if you would say, where is the dark matter in the universe? On average, it's in cluster. And it makes sense because the clusters are supposed to be the latest objects that have been formed in the universe. If we believe the standard model for cosmology, it's hierarchical in the sense that you are forming first small structures, and then these small structures are accreting into larger and larger structures. To much less extent, galaxies are a good tracer of, so to say, the cosmological density of dark matter, but still, it's a very important step, also from the point of view of phenomenology of dark matter. In the sense that was described before, but also in the sense that I want to enlighten in the next lecture. So the story is the story we already heard today. In the 70s, people started measuring with some care the rotation curve of galaxies. So what is the rotation curve of galaxy? You are plotting on the horizontal axis, the distance of a given tracer from the center of the system. And on the vertical axis, you are plotting how fast this object is moving. In some cases, this is just reflecting the fact that this object is moving on a circular orbit. And then you have the centrifugal force, which is balancing the gravitational pull. In some object, this is just a way of conventionally describing the potential well of the object. So there's nothing really on a circular orbit. But so in this first example is referring actually to stuff on circular orbits. And so the first rotation curve, okay, going fast here. There were some first attempt in the late 30s of measuring the rotation curve in Andromeda. So this close galaxy to us. So this was the data from Babcock. So the person that is sort of referred as reference person in this field in the 70s is Vera Rubin, because she organized a program in which these rotation curve measurements were done systematically. So again, so the black dots here are Vera Rubin points for the rotation curve of Andromeda. What should I get out of this? So not much for what regards Andromeda and Vera Rubin points, because you see in this plot, this is again from the paper of Bertone and Hooper. They have plotted one possible model for the rotation curve, which is just based on some photometric model of the stellar disk for Andromeda, which is kind of weird because it has a double nucleus. And then if you stretch this model, you make your theory fits the Rubin-Ford points. They don't fit so much more recent points like this one. In general, it was understood at that time, anyway, that these rotation curves were kind of flat in the outskirts, even in region that was way outside the region where you had the bulk of the mass that was kind of visible. So in this, oops. Okay, so for some reason, so this is a set of nearby small galaxies. This is the gas distribution. This is some radius at which it says 80% of the mass of the gas is within this radius, and that's appearing here. The rotation curve is flattish all the way up to this radius and beyond. Oh, there's something. So, and in general, it went along with this sort of karma. Rotation curves are flat in the outskirts. So this is a compilation. This karma is still around now, but if you look in details, okay, you have rotation curves that are rising, rotation curves that are slightly decaying. On average, they are flat in the outskirts. So then the thing goes like this. You have a given system, so this M33 nearby galaxy. You map the distribution of light in this system somehow. So this is optical light. You associate to this distribution of mass some rotation curve. How do you do that? You're just using the balancing between the centrifugal force and the gravitational pull. Again, you're using Newtonian gravity, and which is telling you that if the system is spherically symmetric, the scaling of the centrifugal force is like the overall mass within a given radius divided by the radius squared. So you see, this is in this exercise, when you saturate M of R, when the mass within R gets constant because there's nothing else you can sum up, then the circular velocity will just scale down like 1 over the square root of radius. Okay? So you have this fall off, this Keplerian fall off, which is the same law that Kepler noticed for the planets around the sun. So this is what you would expect in this specific example, and this is what you measure in this specific example. So you see in this specific example, the rotation curve is slightly rising. And then if you say, okay, it's roughly flat, I have to get this circular velocity flat to match this behavior here. What I need to have is that the mass as a function of radius is growing as the radius itself. So in terms of mass density, I need something that falls like 1 over the radius squared. So on top of this, of the mass that you have associated to light, you're associating an extra component which fills in this gap here. course, has already been mentioned, this works equally well if you are not assuming that this is the correct law, but you are assuming something else. I think that from the point of view of searches of dark matter, however, spiral galaxies are not really the point we want to address. They are not telling us much about particle physics properties. What is telling us more about particle physics properties are other systems which are not rotationally supported, but they are actually, so to speak, pressure supported. So here you have to make an exercise which maybe here is too detailed, but in principle it's not too complicated. You are describing a system as something which is evolving in phase space. So you're following in time coordinates which refer to spatial coordinates and velocity coordinates. And then you derive this collisionless Boltzmann equation, which is like saying that you are conserving a probability of f in time. So the total derivative of f with respect to time is 0, which you can chop up in different components. And either you are able to resolve the system mapping in detail for every object position and velocity, or what you do is to make some kind of averaging of these properties over your ensemble. And then you get to an equation which is one that is a fundamental equation in galactic dynamics, which is called the Jeans equation, which is pretty much the same as the Euler equation for a fluid. And in this equation, you recognize some term which goes with the velocity dispersion, which is a term which is describing the fact that the system is not compressible to infinitely small size. So there is some velocity dispersion associated to that, which is acting as some pressure component. And then, okay, this is very useful because out of this you can map again. Sorry, in this equation there was this pressure term, which is the same here, and then there is this gravity term, gravitational pull. So as in the Euler equation for a fluid, there is a gravitational attraction and a pressure repulsion. So the gravitational attraction, so the gravitational attraction again you can model say by a Newtonian gravity, and the pressure term is what you measure out of the velocity dispersion. And you can do it in some systems which will turn out to be interesting from the point of view of particle physics, which are called dwarf spheroidal galaxies. So these are galaxies which may appear as satellites in spiral galaxies. So there are about 30 of these satellites in our own Milky Way, which have been identified so far, and which are very tricky objects because these are objects that are essentially totally dark matter dominated. So if there's not enough gas to be able to measure it, we can measure the light associated with these objects. And for some of these objects, it's really a bunch of stars, like 100 stars in the full object. You measure out of this tracer, this star, the velocity dispersion, and then you get that this velocity dispersion is rather flat. You can do the modeling through your spherical Jeans equation. And what you find at the end of the day is that you have mass to light ratios, which are really faithful in, say, baryonic to dark matter ratios, which are huge, order of 100 per solar mass per luminosity of the sun. So this number of 100 should be compared to the local number, which is around 2, say 2, 3. So from the point of view of the particle phenomenologist, these are kind of ideal dark matter laboratories. So they contain a very little baryons, very little stars, so very little pollution from this baryonic physics, which was to some extent mentioned that we don't understand very much in galaxies, in massive galaxies, and then they may turn to be important. So I want to end today's lecture with some addressing of what's going on in the Milky Way. I will not be extremely precise here. So in our own galaxy, we have a way lot of ways to measure the gravitational potential well, and then infer the dark matter distribution, again, assuming Newtonian gravity. But on the other hand, these are difficult exercises because you do that from the perspective of somebody that is seated within this potential well. So there are a bunch of methods that have been applied to measure the rotation curve in inverted commas, as I will say in a minute. So how fast gas is rotating the inner part of the galaxy, what is the apparent motion of the galactic center on the sky, what is the motion of stars in the thin stellar disk with respect to the vertical height in the galaxy. There is the dynamics of stars that are sitting in the outskirts of the galaxy. There are stars that you can trace up what is the maximum velocity that a star can have to be gravitationally bound the galaxy. So essentially there's a maximum velocity that you can tolerate. Out of that, you are not in equilibrium, and then essentially this system is not there, and so on and so forth. And this is interesting because it's a field of research which is very active, thanks to the fact that there are probes that have been designed specifically for this issue. So for instance, these very faint objects, 8 of them was known up to the late 90s. Then there was this experiment, which I already mentioned, for the optical light in coma, this lone digital sky survey, which was designed for something completely different, tracing of galaxies far away from us, which actually were making some close scanning of patches of the sky. And out of this close scanning, some interlopers were identified, which are actually dwarf galaxies of the Milky Way. So the number of dwarf galaxies, based on some experiment which had little to do with what searching for dwarf galaxies, so the number of dwarf went from 8 to 30, 40, something like that. And then there are experiments that are going to measure in very fine detail the phase-space distribution of stars in the local neighborhood, like Gaia. So out of this, one can make up a rotation curve for the Milky Way. Again, this is a projection of on this plane of the dynamical information that you get, which are essentially at a different position in the galaxy, the first and second derivative of the gravitational potential well. You can assume axial symmetry, and then plotted this information into a rotation curve. Again, some of these tracers are not in circular orbits. It's just a convention on how to plot the result. But then, okay, also for the Milky Way, what you find is that the description of this overall potential well goes with some part that is connected to the luminous components, so to speak, the baryonic components, the stellar disk and the stellar bulge and gas. And then there is an extra component which somehow is appearing in the outskirt and saturating the shape of the potential in the outskirt of the galaxy. What is the, so out of this you can assess, for instance, how heavy the Milky Way is. It has a total mass which is about 10 to the 12 solar masses out of a budget in, say, standard matter, baryonic matter, gas plus stars, which is, say, below 4 in 10 to the 8 solar masses. I told you that we are sitting in the outskirts of the stellar disk. We are sitting somewhere here, where the stellar disk is already declining. And if I want to make an assessment of how much dark matter I have locally, there are really very different ways to do it. Direct assessment in the sense of direct measurement of the local potential well gives you a number which are not very much constrained. If you put this in a picture in which you are trying to explain all the data simultaneously, then you get numbers which are pretty precise, and is telling you that the density of dark matter locally is about 1/2 of a proton per centimeter cube. The precision of this number is, say, 10%, but maybe there are a number of stars and caveats in this 10%. But that's the kind of number we will use in the last lecture when I will talk about detection of dark matter. Okay, and then I think here I'm switching gear to cosmology, but that I want to do in the next lecture. So, any questions?
Curiosity. If we have to investigate which theories are important to establish that there is dark matter, classical mechanics is the most important in the sense that quantum mechanics is not so relevant, and general relativity in many calculations that you presented is not so relevant. Perhaps with the evaluation of the average density from CMB, there is some calculations that is relativistic, but in general, many things that you presented are classical, not relativistic, or not.
Okay, so if when we embed the standard model of particle physics into the standard model of cosmology, of course, quantum field theory is there at full strength. So that's in the early universe. That's in all the models I will discuss for production of dark matter. So, except for one exception, that is the one for primordial black holes. So, if you're not talking about macroscopic objects, then of course quantum field theory is there. From the point of view of astrophysical observations, I think that fuzzy dark matter has already been mentioned today. That's some kind of manifestation of quantum properties of matter on a macroscopic scale. So I will mention this as one of the possibilities to introduce some kind of energy scale associated to dark matter. And from the point of view of this kind of observations, so the late universe is an environment in which densities are low, and then you start gravitational collapse from small densities, and then essentially you are tracking everything on classical mechanics. So, and again, you haven't seen any relativistic speed here, or so. From that point of view, but of course, the next lecture we start with cosmology, and then how to go from quantum fluctuation to macroscopic objects is, of course, an imprint of quantum mechanics. Yeah.
This question might be a little bit similar, but so we've gone over, all the different ways we have to maybe measure dark matter. Looks like we can infer some things about its density, maybe even the halo profile that it has around galaxies. But of these clues, are there any that, I guess there's a really big gap between noticing these observations and then coming up with a detailed candidate in beyond the standard model of particle physics that would match this. Just from your perspective, what would you say are the most important clues that can lead you to go from inferring something from these observations to an actual quantum field theory model of what might be?
So I started today's lecture telling you that okay, I'm a particle physicist, and then what a particle physicist want to address is an energy scale and an interaction scale. And the next lecture is going to be all about this, in the sense that I will tell you a little bit of what you learn from cosmology, and then essentially there are what I call the 5 golden rules that you can extract out of astrophysical and cosmological observation, and which tell you a little bit on what track you can be on the particle physics or matter side. Yeah. Sure.
Actually, I have a very similar question.
Yeah.
And I want to hear your opinion as a particle physicist. So apparently, these observations, cosmological observations, give very little constraints apart from a very large range of mass for the particle particles. In a hypothetical scenario where we have a missing energy signature in a collider, what are the next steps for determining the properties of the particle?
So I think that okay, the standard answer to this is that you should go from the LHC to direct detection and really confirm that the kind of mass scale that you are testing at LHC is the mass scale which impacts on direct search for dark matter. Of course, there are also indirect ways of searching for dark matter, and which goes through this multi-messenger program that I was trying to introduce. So I don't know, the fact that dark matter particle may decay, the fact that dark matter particle may annihilate in pairs, the fact that dark matter particle may eat the interstellar medium, the fact that the dark matter particle may, we go to gravitational waves, change the equational state of a neutron star. All of these are, so to speak, sectorial, in the sense that you are percolating to specific portion of the parameter space of a model or some direction in the modeling. But I think that once we get a benchmark, you should look in this direction, then everything will get more clear and faster. So because there are really many potential techniques that one could implement to have observable effects. Yeah.